We have been talking, once I have a pen, we have been talking about hybridization. We talked about carbons that make single bonds. Those are sp3 hybridized carbons. We talked about carbons that make double bonds. Those are sp2 hybridized carbons. The last one in the series are sp hybridized carbons. And I think I have a section. This is section 1.9. Break it really fast. Section 1.9, which is sp hybridized carbons. I'm going to put it in a box, even though it's funny to have a circle in a box next to each other, because I put the other ones in boxes. Darn it. What we've been doing is saying, hey, the electron configuration of carbon is not working out for us. Carbon has in its valence shell a 2s orbital and 3 2p orbitals. There are 2 electrons down here and one electron apiece in this top shell. I'm missing a couple electrons from carbon's overall structure. Where are they? Down here, right? First question on the quiz. So we're not going to count those right now because those are valence electrons. Those are not part of the valence. So I'm only looking at the valence electrons here. In my first treatment, I said I'm going to mix all of these together, sp3, and get 4 hybrid orbitals, 1, 2, 3, 4. In my second treatment, I said, you know what I'm going to do is just take the 2 p orbitals and the s, so that's sp2, that left me with 1 p orbital that was unhybridized. This last one, I'm going to take 1 p and 1 s to hybridize. So I'm going to form how many sp hybrid orbitals? 2, because I took 2 orbitals over here. So I'm going to make 2 sp hybrid orbitals over here. What's left over? What did I not touch? 2 p orbitals. So I'm going to put 2 orbitals that are slightly higher than that. Again, these are all pretty close in energy. So I'm going to put 1 electron here, 1 electron here, 1 electron there, 1 electron there. An sp hybrid orbital looks the exact same as the others. It's just a little bit more blobby because it's a little bit more circular, but they all have this kind of exclamation point sort of look to them. Sp hybridized carbons have 2 p orbitals. So this is where the drawing gets real funky. As an example of this, what we're going to do is draw ethine. Notice in the last one that we drew, it was ethene. You don't need to know this yet, but this ending, the suffix yne, is going to tell us that there's a triple bond present. When we have an ene as a suffix, that's going to tell us there's a double bond present. If we only have single bonds, we're going to use ane. But we'll get more into that later on. Ethine has a chemical formula of C2H2. So just like you guys all mastered for me on this quiz, first thing I want to do if I'm going to draw this structure is count out the valence electrons. How many come in from carbons total? 8. How many come in from hydrogens total? 2. 8 plus 2, I think, is 10. So I have 10 electrons that I can play with here to try and build this thing out. Carbons like to be in the middle. So let's put a carbon here. 1, 2, 3, 4, 5, 6, 7, 8. Put a carbon over there. 2, 4, 6, 8, 10. Maybe a hydrogen here and a hydrogen there. Ethine. I worked really hard on it. Yesterday's lecture was so embarrassing because I got all these structures wrong, but I spent all night working on my Lewis dot structures, and I'm really, really proud of this one. What do you guys think? You're mean to me. Generally, just as a group, you're just like, it's just disrespectful. What's wrong with my structure? Which octet rule? Carbon. That carbon only has 4 electrons. Are you kidding me, Dr. Green? Get out of here. Do you even know what you're talking about? Can we bring someone in who has a clue what's going on with organic chemistry? No, this is not right at all. we're gonna have to share a bunch of electrons. If you draw a structure that has all the correct number of electrons and you end up with a carbon with 4, you got to share like a lot. What we did previously, actually, let's leave the X's on there because that's just horrendous. What we did previously is said, well, let's, instead of sharing 1 pair of electrons, let's share 2 pairs of electrons. That would make a double bond, right? If I try and draw this out, I could be cheeky, but it's not going to work. If I put just a double bond in there, not everyone's going to get their octet. So what I'm going to do is share 3 pairs of electrons between these carbons. That looks crazy, right? But if I do that, 2, 4, 6, 8, 10 electrons, and then I count out how many are surrounding each carbon here. There's 10 on this side, and there are 10 on this side. Huzzah. I have shared these well enough to where everybody has 8 electrons. And then the hydrogens have 2, right? And just put 1 bond to hydrogen, you'll be good. If you ever put 2 bonds to hydrogen, you've done it wrong. That's the rule of thumb. That looks silly, so let's draw this not as a Lewis dot structure, but as a Kekulé structure, which looks like this. This is an sp hybridized carbon. Both of those carbons are sp hybridized. sp hybridized carbons have a bond angle of 180 degrees. They are linear. And thus concludes the 3 numbers I need you to memorize. So let's put them all together in a delicious hybridization sandwich. If you are sp3 hybridized, you have a bond angle of 109.5. What shape does that give you? Tetrahedral, very good. If you're sp2 hybridized, you have a bond angle of, not you, 120, which gives you a shape of what? Trigonal planar, very good. And if you are sp hybridized, you have a bond angle of 180, which makes you linear. Make sense for the bond angles? Let's talk about the orbitals that make up this bond. A double bond is made up of 1 sigma and 1 pi. A single bond is made up of just 1 sigma. A triple bond is going to be made up of 1 sigma and 2 pi bonds. The way we're going to do this is we have to use some dashes and wedges to make this work out. We're going to have p orbitals that are up and down in the plane, and we're going to have p orbitals that are coming in and out at you going this way. So when you look at it from the side on, it's going to be p orbitals like this, p orbitals like that. So if you look down the barrel of this thing, you're going to see a p orbital going one way and a p orbital going the other way. I'm going to attempt to draw that for you, and you guys are going to love it because it's so easy. Draw it nice and big on your page because it's a mess. There's a carbon. What orbital is this? sp, very good. A carbon on the other side is going to have another sp orbital to make what kind of bond? A sigma bond. The head-on overlap of 2 orbitals, in this case, 2 sp orbitals that are making that bond. Okay, now we also have, let me keep this in blank. I'll try and color code everything here. We also have a p orbital here and a p orbital here. And if they are phased correctly, meaning that they are both shaded up or both shaded down, those p orbitals can overlap. And I'm going to draw 2 lines here, but I'm actually only making 1 bond. What kind of bond is that? Gotcha. They drift way too far. What kind of bond did I just make? Pi bond, right? 2 lines, 1 bond. What I've drawn for you so far is a double bond, 1 sigma, 1 pi. There is an additional p orbital on this carbon. Right? So I've drawn one of those p orbitals. There's another one. And so what I'm going to have to do here is to show you it coming in and out of the page, I need to use kind of a dash wedge notation. So I'm going to put one of these lobes on a wedge and one of these lobes on a dash. Wedge, let me move this out of the way. Edge. Dash. Can we see that kind of? I think maybe it's easier with my little hand puppets here. P orbitals facing up and down, that's in blue. P orbitals coming in and out of you, that's in green. Pi bond going this way. Pi bond going this way. A triple bond equals 1 sigma bond and 2 pi bonds. Yeah. I did not draw the hydrogens in there because it gets real messy, but the hydrogens would be going out this way and out that way. So I'm drawing you just the carbon-carbon bonding. I'll put it on there, but you're not going to do it.
So that's the old happens just between carbon.
No, it happens the other way as well. So let me put it in fuchsia. So this carbon has an sp orbital facing this way. That's one of these sp orbitals. There's another sp orbital, right? It's facing the opposite way. And that's what's bonding to the hydrogen over here. I'm just focusing on the carbon-carbon bond though. So if I pull the hydrogen out of there, I have now shown you every orbital around this carbon. Let me try and spell them out. This carbon, as I showed you up there, has 2 hybrid sp orbitals and 2 p orbitals. One of the sp orbitals is going this way in black. One of, oh, those look like the exact same color. On my screen, well, no, they do look pretty similar here too. On my screen, it's much more pink. This is pink. So an sp orbital going this way in black, an sp orbital going that way in pink, a p orbital up and down in blue, and a p orbital in and out of the page in green. 4 orbitals coming off that carbon, making 4 different bonds. I'm going to take this other one off of there because it just gets, it's complicated without putting the hydrogens on there. If and when I ask you to do this, I won't do it on the quiz at this point, but on these, actually, sorry, SP is fair game for the next quiz because we're covering it for quiz 2 material. I should make a bigger stink about that. Put little lines in your notes about what was quiz 1 and quiz 2. So everything from section 1.9 to wherever we get before quiz 2, that's quiz 2's material. Everything from the beginning of class until we get to exam 1 is exam 1's material. So if you put little lines in there, you'll always know kind of what sections to fall into. So if I ask you to do this on the next quiz, I will specify, here's a molecule, draw for me the carbon-hydrogen bond, or in this case, draw for me the orbitals of the carbon-carbon bond, not the entire molecule, because it just gets too messy. Questions about sp hybridized carbons? Yeah. The quiz 1 was 1.0 to 1.8. Well, up to 1.9, however you want to stylize that. Not inclusive of 1.9. Okay. Everybody good and confused? Yeah.
So when you write 4 electrons on the top of the note, so that means when 2 so when molecule bonds happen, so that 4 is like covalent, covalent, the valence electron from both of them.
Correct. So what I'm doing on this very top thing up here is I'm saying that the valence electrons in carbon in a ground state configuration look like this. Right. So these are the exposed electrons in carbon in its ground state configuration. For only for carbon. Right. So when carbon starts to make bonds, it has these electrons at its disposal. When carbon goes to make bonds, it has 4 valence electrons, which means when it goes to make a bond to something else, it has to bring an electron as well. If you're carbon and I'm a hydrogen and we're going to form a bond, you're going to reach out with 1 electron and say, okay, let's do this. And I will say, oh, nice to meet you. Here's my 1 electron as well. we form a sigma bond when we do that. When we share those electrons, that gives carbon its full octet. The carbon doesn't bring an octet with it to the molecule. Now, in its ground state configuration, it doesn't explain this, right, because we see this triple bond feature of a sp hybridized carbon that we can explain. This molecule is not explained by the ground state configuration. So that's why we're doing this hybridization discussion. Is when we see carbons make different shapes, we have to figure out something happened to the electron where they're at. Hybridization is our answer to that. Let me give you a shortcut now that I've given you the actual theory behind all of this, which is you can just count the number of bonds to a carbon to determine its hybridization. So let's use a test molecule here. I'm going to leave dashes and wedges out of it just to make it a little bit easier. A question that I will absolutely be asking you at some point, probably on quiz 2, is label the hybridization of each carbon in this molecule. So occasionally you'll see me write up this thing that says try this. What I want you to do is we're going to take just a minute, copy that structure down, and then I want you to put an arrow to every carbon in there and tell me, is that carbon sp3 hybridized, sp2 hybridized, or sp hybridized? I'm going to show you a shortcut of how to do this. So I got a couple carbons in here. There, one there, there. When you are trying to take on something like this, you can rely on a couple different shortcuts. One we've established is the carbons that only have single bonds surrounding them are sp2 hybridized. Carbons that have double bonds surrounding them are sp2 hybridized, and carbons that have triple bonds surrounding them are sp hybridized. That's one way to do it, but that only lets you have carbon in your belt. We're also going to do this for nitrogen, oxygen, and other atoms. So the shortcut you can do is count up the electron domains surrounding it. What I mean by electron domains is how many different areas can you find electrons around an atom? This carbon has 1, 2, 3, 4 electron domains around it. 4 electron domains. What we're going to do is say that that is sp3 hybridized. And the way you can shorthand remember this is if you put an imaginary 1 above the s, 1 plus 3 equals 4. sp3 means 4 electron domains. How many electron domains around this carbon? 3. I have a double bond. I'm going to count that all as kind of one area where electrons gather. So 1, 2, and let me just circle them. Maybe that's easier. 1, 2, 3 domains are on that carbon. If you have 3 domains, your sp2 hybridized. The way you remember that, again, put an imaginary 1 above the s. 1 plus 2 equals 3. 3 electron domains. How many electron domains are on an sp hybridized carbon? 2. This carbon has 1, 2 electron domains around it. 2 electron domains. Equals sp hybridized. So this carbon is sp hybridized. How about this carbon? Also sp hybridized. I missed one. Zootalor. What's this one? sp2, right? It has 1, 2, 3 domains around the outside, so that is sp2 hybridized. Does that make sense to everybody? It's going to make us faster when we start using things like nitrogen and oxygen, which have lone pairs. Lone pairs are going to count as electron domains. If an oxygen has 2 lone pairs, we're going to count each one of those as an electron domain separately. That'll speed us up when we're assigning hybridization to a bunch of different things. I'll put this on here. I generally don't like putting on tables. If you don't want to copy down a table, this is absolutely in your book. So I'm going to make a really messy, quick table here. But you're going to be able to find it around section 1.9, probably at the end of section 1.9, where they have a series of molecules. See why I don't do tables, because I'm bad at them. We're going to talk about the CC bond strength. And the CC bond length. The molecules we're going to use are ethane. There's these suffixes I was talking about. Ethene and ethine. Ethane is a CH3 bound to a CH3, single bond. Ethene is a CH2 doubly bound to another CH2. And ethine is a CH triply bound to another carbon. So single bond, double bond, triple bond. What do you think is happening to the bond length as we go from ethane to ethene to ethine? Are the bonds getting shorter or are the bonds getting further apart? Shorter. Why? You're right.
It's more like attraction.
Yeah. Right. So if you guys are one atom and I'm another atom, and you put 2 electrons between us, we are drawn to those electrons. I don't want to be near you guys because you're positively charged and I'm positively charged. Right. Sometimes, let's just be honest, 2 positively charged fixed bonds. We don't want to be near each other, but we do want to be near the electrons that are between us. You put 2 there, we both go, ooh. You put 4 there, we go, this is really nice. Put 6 electrons there, we're going to just keep getting drawn in closer and closer and closer to those electrons. More electrons, more bonding interactions, shorter bonds. Shorter bonds are stronger bonds. They are harder to break. When I go from ethane to ethine, I go from 154 picometers to ethene, 134 picometers, to ethine, 120 picometers. Itty bitty teeny tiny meters. Bonds are getting shorter as we go down the series. How about the bond strength? Remember, the bond strength is how much energy do I have to put in to break this molecule up? If I want a CH3 on one side and a CH3 on the other side to break apart, how much energy do I have to put into the bond to break that apart? For ethane, it's 377 kilojoules per mole. For ethene, what would you predict it would be? Higher. How much higher? I think a reasonable guess would be twice as much, right? So ethane has 1 bond. Ethene has 2 bonds. So Ethene should be whatever 377 times 2 is, right? Twice as strong. I did the math. I'm not in my head. If you take 377 times 2, you get to 754, which is not the bond strength of ethene. The bond strength of ethene is 728. It should be 754, right? Twice the single bond strength, but it's not. Why? Why is ethene not twice as strong as ethane? Yeah, sigma bonds are awesome. This is where you want to be if you're an electron, right? Sigma bonds super strong. If you had 2 sigma bonds, it would be twice as strong. But remember, one's a sigma, the other one's a pi. That is a substandard bond. This is a way of showing you quantitatively that pi bonds are not as strong as sigma bonds. So this is something that the MCAT loves to do, where they'll play with words on this. They'll say, which bond is stronger, a double bond or a single bond? A double bond is stronger, right? It takes 728 kilojoules per mole to break this molecule apart. Which bond is stronger, a pi bond or a sigma bond? A sigma bond is stronger than a pi bond because a double bond is sigma and pi together. You see the sinister question coming your way for taking the MCAT? They will ask you something about that. They love doing that. They are jerks. You hear me, AMAC? You're mean people. Stop doing this. This is not how we should mint physicians. More to say on the MCAT later on. When we go from a double bond to a triple bond, you'd think, okay, well, it's whatever the difference is between these two. So there's 351. If I take 728 minus 377, that's 351. You should say, well, a pi bond is worth 351 kilojoules per mole. So if I take 728 plus 351, I would get to 1079. Spoiler alert, this is not 1079, it's 965. So that was probably confusing with all the numbers in there. I didn't get my full double over here. I got some unit smaller than that. And then I thought, well, I could predict this next one by taking that unit, adding it to 728, but it was even less. So the bond is getting stronger, but it's like as we add more interactions on there, they're just getting like more and more substandard. The deal with a triple bond is it's just getting too crowded. We have too many cooks in the kitchen. This is where you want to be. This is okay. Who invited these dudes? Right? Too many electrons in between these two atoms. Electrons do like nuclei, right? So we're putting electrons between two nuclei. That's great. But there's a lot of electrons showing up now to this party, and it's just getting too crowded. So triple bonds are the strongest bond, but triple bonds are actually the most reactive of this series. I can do chemistry to ethine much more easily than I can do chemistry to ethane. But I don't target the entire bond. I don't try and break all 3 bonds at a time. I break one of the pi bonds. Breaking that third pi bond or breaking that third interaction, one of the pi bonds, super easy. Breaking another pi bond, that's harder. Breaking a sigma bond, really difficult. Want to know why we can't get rid of plastics? Guess what they're made of? This guy. When we make polymers, we're making them out of carbon-carbon single bonds. Those suckers are strong. Nothing breaks those down. Right? And that's the problem. We got really good at making carbon-carbon bonds. Yay! Wait a minute. Now we have to like unmake those bonds. Really hard to do chemistry on them. One of the few times I'll put up a table on here. You don't need to copy any of this down. It's in your book, but I had it up here just to make that point. As we add more bonds, they become stronger and shorter. But the picture is more complicated because those components of the bonds matter. And we're going to focus on that chemistry throughout the rest of this class. Questions about that? Okay. As promised, let's talk about hybridization of some other stuff that's not carbon. I don't know why we have to talk about things that aren't carbon. I find them generally unimportant. But I'm supposed to tell you about hybridization and lone pairs. I'm just kidding. Some of the other atoms matter. Just nitrogen and oxygen and halogens, though. All the transition metals, they can go away. Show you 2 different molecules. That looks awful. We could draw it well for you. And that looks about the same, but here we are. Anybody know the name of this NH3? What is it? Ammonia. Ammonium would be if it had another hydrogen up here, that'd be NH4 plus. So that's ammonia. How many electron domains does ammonia have? Who thinks 3? Who thinks 4? Who's not going to vote, no matter how much I put pressure on you to do so? A couple of you. It has 4. Nitrogen has a bond here, here, and here. And then that lone pair also counts. There are 4 electron domains. That nitrogen is sp3 hybridized. How about water? How many electron domains around that oxygen? 4. What's the hybridization of that oxygen? sp3 hybridized. 1, 2, 3, 4 electron domains, sp3 hybridized. Lone pairs count. Or here, I'll just do it this way. Count lone pairs. As electron domains. Easy enough? Good. Try this. Give me the hybridization for each atom with an arrow pointing at it. Now accepting brave souls. What you got, Zachary?
I got SB2 on both ones on the left.
So the oxygen, you got sp2. And let's put that's weird for it to be in blue and red. sp2. What do you say sp2 for that oxygen?
It says 3 electron domains.
3 electron domains. 1, 2. Now I will count these in blue. 1, 2, 3. You see that? And then down here, you said that this was also sp2. Same reason. 1, 2, 3 electron domains surrounding that carbon, sp2 hybridized. Somebody else over here. sp3 for both of them. Yeah, so I didn't draw these out for you, but you know there are 3 bonds to these hydrogens, right? So carbon has 1, 2, 3 on the hydrogen, 4 down here, so sp3. And then this nitrogen, how many domains? sp3 because it has 1, 2, 3, 4 domains around it as well. Count the lone pair as the domain. You'll be good to go. Everybody feel a question coming their way on quiz 2? How easy would this be? I don't teach this class, but if I did, I would think that if you could like put up a bunch of different structures and have arrows like this, and then the students could fill in the arrows, it would be so easy to grade and also test their ability to like judge hybridization. Right? That's a question you would do, I'm sure. Just spitballing here. When's quiz 2? Next Tuesday? That would be like a good next Tuesday kind of question. I feel like not a Monday question, but next Tuesday, that'd be a great question. Some of you are mildly entertained and other of you want me to move on with it. Let's talk about one last theory of bonding, which is the most complicated and one we just need to be aware of kind of in the background. We started off with each atom has its own individual electrons and their own configuration. They bring those electrons to other atoms. They make valence bond, what we call valence bond theory. Then we said, it's not working out. Carbon's electron configuration doesn't explain all these funny shapes it makes. So we had to talk about hybridization. That was our kind of our next level of like, let's get a little more complicated. Recently, and when I mean recently, within my lifetime, we figured out that electrons are crazy. There's this thing called the particle wave duality, where electrons act as particles and waves at the same time. I won't go into all of it, but it is wild when you start thinking about the potential outcomes of that. Well, what that means is that electrons can combine together like waves in the ocean. If this whole room was flooded right here, and I drop a pebble, a wave would be emitted from the pebble. If you dropped a pebble on that side, you would have a wave come over and the waves could combine together. That's something that electrons can do when a molecule forms. So we have to talk about something called molecular orbital theory. It's not just me bringing my atomic orbitals and matching them with your atomic orbitals. It's here's my atomic orbital, here's your atomic orbital. Oh man, we've made something new. The electrons aren't mine and yours anymore. Now they are ours in this beautiful collection. That is called molecular orbital theory. Or MO. Molecular orbital theory describes electrons around an entire molecule. Not just atoms. We've actually been talking about some molecular orbital theory. I've snuck it in. We aren't going to talk about sp or sp2 or sp3 hybridized orbitals because those belong to individual carbons. Instead, we're going to talk about the shared electrons. We've been talking about shared electrons. A sigma bond is a type of molecular orbital because a sigma bond is shared between two atoms. A pi bond is a molecular orbital because it's shared across multiple atoms. The only thing that's a little bit different is we are going to introduce this concept of bonding and anti-bonding orbitals. So let's do it first for H2. What I'm going to do is show atoms on the outer edges here. I've drawn a structure like this for you before. This is a hydrogen with a 1s orbital and a hydrogen with a 1s orbital. So two hydrogens floating out in space, independent of each other. How many electrons are in these 1s orbitals? One apiece. One there, one there. When the two hydrogens come together, they are going to share their electron density to drop down. So this is an atomic orbital. This is an atomic orbital. So my two atomic orbitals are going to mix to make a molecular orbital. That molecular orbital is called a sigma bond. But waves have this weird thing where they can interfere with each other constructively or destructively. Anybody have noise canceling headphones? Have you ever put those in? It's like so disorienting. You put them in and it's kind of like, especially if you're on a plane, right? The plane is like the worst part. Or, I mean, it's kind of nice, but I feel like I'm going deaf when I put them in. You hear the white noise of the jets, right? You put them in and it just goes silent. It's not that they're plugging your ears from any noise hitting. what your headphones are doing, which is pretty genius, is they're saying there's a certain wavelength coming in and attacking your ears at a basal level. I'm going to make a wave that is opposite that and put it into your ear. So it's actually putting more noise into your head, not less. But the noise cancels out the other noise that you hear. So the noise canceling is, I've got a wave going like this, so I'm going to put in a wave going like that, and overall our head is going to feel nothing, which is why you get that kind of sort of feeling when you put them in. If you haven't done noise canceling headphones, you should try it sometime. It's really, I think, unnerving. This is a constructive interference. I have a wave coming together, so the other wave matches it, and the wave gets twice as high. They can also destructively interfere with one another and go to a higher energy state, what we would call a sigma, that's a sigma star, or an antibond. If we put electrons into an antibonding orbital, that would discourage these two atoms from binding together, because now we have energy that's been lowered, but we're also having energy that's being picked up a little bit. For hydrogen, there's only one electron in each one of these. So off-ball principle says send them to the lowest orbital first. The sigma star, the antibonding orbital, is empty. There's nothing up there. So when two hydrogens meet, they form a bond. Good news. If I were to take an electron gun and shoot it at an H2 molecule, the only place to put in electrons would be up here. So if I added H2 with an electron, so H2 minus, I would fill in one of these antibonding orbital spots up here, and the hydrogen bond would start to weaken a little bit. I shoot it with another electron, I put two electrons up here, now they want to fall apart. So H2 2 minus does not exist, because the second that happens, the hydrogens fall apart. That's kind of confusing though, so let's look at it instead for something like helium. Helium-2 would look like this. So helium's on the opposite side of the periodic table, right? Hydrogen is, you'll see it, hydrogen's over there. Helium is over here. They both have just a 1s orbital. The only difference is helium has 2 electrons in that 1s orbital. So here's a helium atom. Here's a helium atom. 1s. 1s. In hydrogen, I put 1 electron here. In helium, I'm going to put 2 electrons there, because that's the valence electrons it's bringing. Same thing over here. 2 helium atoms bump into each other. And they say, ooh, let's share our electrons to make a molecular orbital. I'm going to draw the same picture I did over here. 2 of those electrons go down. They make a sigma bond. Yay. But that's not all the electrons I have in my system, right? That's only 2 of the 4. So 2 electrons go down, 2 electrons also go up to the sigma star. What that means is when a helium atom runs into another helium atom and they go for this handshake, the handshake is as much a slap in the face as it is a handshake. They help each other, but they hurt each other as well. So do 2 helium atoms form a bond? No. They bounce into each other and they're like, that wasn't great. I'm, you know what, I was fine on my own. I don't need you. When 2 hydrogens bond together, they're like, oh, thank God I found you. I was freaking out. I was so high energy. Now I formed a bond with you. We dropped down. I formed my sigma bond. Excellent. For that reason, if I had a tank of helium gas up here, you know, the stuff you fill up in balloons, make your voice really high, I don't know if you know this, there's actually a helium shortage. So next time you have a kid's birthday party and you see helium balloons everywhere, like we use helium for medical equipment and other stuff as well. So like, maybe take it easy on the helium balloons. When you open a tank of helium and you fill up the balloon, it's helium atoms that are in there, not He2, just helium atoms bouncing around. That's part of the reason it's not very dense at all. It's part of the reason that it floats. If I had a tank of hydrogen in here, I wouldn't open it up because I could make us explode like a Hindenburg. But if I opened a tank of hydrogen in here, H2 molecules would come out, not hydrogen atoms, H2 as a molecule. Molecular orbital theory tells us why. H2 forms, He2 does not form. And it's because of this only constructive interference versus constructive and destructive interference over here. For our purposes, I just want you to know that this theory exists. In OChem 2, we'll talk more about using these orbitals to promote reactions. So if I wanted an H2 molecule to break apart, what I'm going to do as a chemist is have a molecule that can send electrons into this orbital. If I want an H2 molecule to break up, I need to target the sigma star of H2, put electrons into it, and then that'll allow it to break apart. So I would use an electron-rich thing like a transition metal to break apart hydrogen gas. We do that. That's too advanced for where we're at right now. So the thing I want you to know is molecular orbital theory tells you about how when two atoms share electrons, they turn into this new thing, not s orbital, but now it's the sigma bond. That is a different entity. And when you form a sigma bond, you also form a destructive potential, which is what we call the sigma star. There's a yin and yang to every bond that you form, the bond and then the anti-bond. We can do it with pi bonds as well. You have a pi bond and a pi star bond, anti-bond. That makes sense? This is again, molecular orbital theory, MO theory is very deep calculus. So we are just barely skimming the surface here. Anybody familiar with Schrodinger's equation? Never heard of like Schrodinger's cat, anything like that? Okay, then I will spare you. This is Schrodinger's equation solves for this thing. The last thing I want to tell you about is I want to make us faster at drawing structures. So this is kind of a move away from talking about bonding theory. We have been learning how to draw structures with dots and with lines. Lines are faster, still way too slow though. So the last section here is section 1.12. 12, which is drawing chemical structures. I'm going to draw a structure up here. I want you to wait until I'm done drawing it, and I'm going to time you all. So put your pens down real quick for me. Okay. On your marks. Get set. Go. Done drawing it, put your pen down. I like it with gusto. Like that. Okay, 22.94 seconds. We're using tenths of seconds here. This is benzene. Benzene is kind of a base level structure for us. If it takes you 20 seconds to draw a benzene, it's going to take you hours to draw anything else in this class. So instead of drawing benzene like this, we are going to start drawing benzene. Don't draw it yet. Like this. Pick up your pens. Ready, set, go. Put it down when you're done. .9 seconds. Right. You're going to be a lot faster than that. So this is one of the first benzenes that you've drawn. I have just conveyed to you the exact same information from this structure and that structure. So I need to teach you some rules so that you see this structure the same way that you'd see this one. This is what we call a line or Kekulé structure. This is what we call a skeletal structure. Skeletal structures are going to be your best friend. At first, they're going to freak you out. And I still recommend drawing line structures kind of next to skeletal structures, but I want you to spend the next few days. We're going to transition over from this slower, bulkier version to this leaner Ferrari version of drawing structures because it's just going to make our lives much easier. Here are some rules for skeletal structures. Number 1, you may notice in the skeletal structure, I didn't draw a single carbon, which is kind of funny, right? This is organic chemistry. I should draw only carbons, right? If I was like, my view of the world is just carbon, all the other elements are not carbon. But the problem is there's so many carbons that we need to have a shorthand for them. So carbon atoms aren't shown. They appear at the ends of lines, angles, and intersections of lines. So how many carbons in my structure on the left? 6. I'm going to represent those 6 carbons over here, in this case, as 6 angles. And put some numbers on here. 1, 2, 3, 4, 5, 6. Carbon 1 is shown by an angle there. Carbon 2 there. 3, 4, 5, 6. Everywhere you see a bend in a line, that's a carbon. I can also represent these by crossing lines or by the end of a line, and I'll show you that here in a second. With me so far? Other thing you may notice that's missing, hydrogens. I didn't draw any hydrogens in the structure. Carbon and hydrogen are best friends. Every time you see a carbon, there's probably a couple hydrogens on there. It is possible for a carbon to not have hydrogens, but generally speaking, where there are carbons, there are hydrogens. Hydrogen atoms bound to carbon are not shown. You need to mentally supply the correct number. What does that mean, mentally supply the correct number? It means give the carbon enough hydrogens for that carbon to have an octet. So let's take carbon number 1, for example. Carbon number 1 in my structure has 1, 2, 3 lines coming off of it. That means how many electrons are around that carbon right now? 6 total electrons shown explicitly on carbon 1 right now. You see that? 2, 4, 6 lines coming off of that bend. 6, you may notice, is not 8. In order for carbon number 1 to have a full octet, it must have 1 hydrogen. So I assume there is 1 hydrogen on there to make sure that that carbon has an octet. That's shown over here more explicitly. I'm going to mentally supply the number of hydrogens I need to each carbon to give it an octet. Rule 3. Show all non-carbon atoms. And while you're learning the ropes here, draw all your lone pairs. There's a bunch of other little rules to this, but we'll start with these as we're starting to learn how to draw skeletal structures. Before I send you on your way, I'll give you one more thing to try here. You can go ahead and draw this if you want with me. I'm not going to time you anymore. So this is the correct way to draw a structure. Notice what I've done is I drew in my nitrogen. I drew a lone pair on it. Hydrogens bound to other atoms must be shown. So if this nitrogen has a hydrogen, I have to show it explicitly. I didn't draw any of the other hydrogens in here. What I want you to do is draw all of the other hydrogens on this molecule. Show me them explicitly. And not homework, do it right now. How many hydrogens here? No, I'm gonna get these names down. What's your name one more time? Emily. How many hydrogens here? One. How many here? None. Here. One. 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 Let's just keep going. You're doing great. How many here? Two. How many here?
No, no.
One. Am I missing any others? Down here, that's the end of a line, right? So there's a carbon there, which means it has 3 hydrogens attached to it. Same thing over here. When a carbon has 3 hydrogens attached to it, we call that type of carbon a methyl. You don't need to know this yet. I'll cover it a little bit later on. But if I took that blue circle off of this molecule and I replaced it with a hydrogen, that core structure is something called amphetamine. So if I replace a hydrogen on amphetamine with a methyl group, what do you think the name of that molecule is? Methyl amphetamine, but nobody calls it that. We instead call it meth, right? So the meth that comes from this is the methyl group that's attached here on the end. We'll talk a lot about drugs in here. I am not endorsing drugs, but they are all organic products. Stay tuned. I'll see you all tomorrow. And keep in mind, if you do not want to join me in person, you can join remotely. The way you can do that is on our Blackboard site. I have in the syllabus, I need to put it on the announcements, but on the syllabus, there is a link right here. That link will give you access to the class where you can join me remotely. I hope to see you in person, but if not, I will see you on the screen for Thursday. Have a good one.